Hello everyone. Today we will be presenting our power system case study, which is the analysis of the IEEE 9-bus power system. In this presentation, we will discuss the overview of the IEEE 9-bus system, its components, application, and the analysis performed to understand its power system behavior. So we are from Group 5, and our group members are Wee Jian Hui, Chu Wei Xiang, Abdul Azam, Purushottam, and Darren. Without further delay, let us begin with the introduction and the system overview of the IEEE 9-bus power system. So the IEEE 9-bus test system, also known as the WSCC3 machine 9-bus system, is one of the most widely used benchmark models in power system engineering. It represents a simplified electrical transmission network that captures the essential characteristic of a real power system while remaining compact and easy to analyze. It was developed to provide researchers and engineers with a standardized power network for testing and comparing different analysis methods. Since the same benchmark is used worldwide, simulation results can be compared consistently and fairly across different studies. So because of the advantages, the IEEE 9-bus system is widely used in university, research institution, and commercial power system software as a reliable benchmark for power system analysis. Now moving on to the system configuration. So the system consists of 9 bus, 3 synchronous generators, 3 load buses, 3 transformers, and 6 transmission lines. Operating on a 100 megavolt ampere base, which is the standard reference used for per unit calculation. The buses are classified into 3 types according to their operating functions. So bus 1 is the slack bus, which maintains the reference voltage and balance the overall system power. Buses 2 and 3 are PV bus, where the generator output power and the voltage magnitude are specified. The remaining buses operate as PQ bus, where the active and reactive power demands are defined. So together, these components form a simplified but realistic transmission network that is suitable for various power system studies. So now moving on to the components and power flow, which illustrate the main components of the IEEE 9-bus system and how electrical power flows through a network. So the process begins with the generators, which produce electrical energy. The generated voltage is then stepped up by the transformers, allowing electricity to be transmitted more efficiently with lower power losses. So the electrical power is then transferred through the transmission lines with connect to different buses throughout the network before finally reaching the load buses, where the electrical energy is consumed. So throughout this process, the buses act as a connection points between all the components and provide locations where important electrical quantities such as voltage and power flow measured during analysis. Although this is a relatively small system, it contains all the essential components found in a practical transmission network. And now, this slide presents the overall workflow of our case study. So after introducing the IEEE 9-bus system and understanding its configuration, the next stage is the network analysis, where the electrical connection between generators, buses, transformers, transmission lines, and loads are calculated. So this is followed by the power flow analysis to evaluate voltage profile, power distribution, and transmission losses during normal operating conditions. The next, the fault analysis investigate the system behavior under fault condition, while the stability assessment evaluates whether the system can be maintained stable operation after a disturbance. Together, this analysis demonstrate why the IEEE 9-bus system is widely used as a benchmark for evaluating power system performance and validating new engineering methods. With that, I have completed the system overview, and now I will hand over to my teammate to continue with the network analysis.
Now I explain the network analysis that we have used for our WSCC 3 machine 9 bus test system. So this system is actually suitable for our case study because it contains the main parts of a power network, which includes generators, transformers, transmission line, and load buses. So the system is based on a 100 mega VA base with the frequency of 50 hertz and a nominal bus voltage of 230 kilovolts. So in terms of our bus classification, as you can see in the table, bus 1 is selected as the swing bus, which act as the reference bus. Bus 2 and bus 3 are PV generator buses, while bus 5, 6, and 8 are the PQ load buses. And the remaining buses, which are bus 4, bus 7, and bus 9, act as the network buses that interconnect the generators and loads. So you can also see figure 2.1, where we have showed the test system diagram. Next, this slide shows the main data used for our network analysis. So as you can see in our slide, there are a few tables. So these tables are divided into load data, generator data, transformer data, and transmission line data. So the load demand is located at bus 5, 6, and 8. So the total power demand is about 315 megawatts, while the total reactive power demand is 115 mega. From the generation side, there are 3 generators. So G1 supplies 72 megawatts, G2 supplies 163 megawatts, and then G3 supplies 85 megawatts. So this gives a total power generation of 320 megawatts. And the transmission network consists of 6 main lines: 4 to 5, 4 to 6, 6 to 9, 5 to 7, 7 to 8, and 8 to 9. So each line is represented by resistance, reactance, and also line charging admittance. So these parameters are important because they determine how our power is transferred between the buses and how the Y bus matrix is formed. Finally, this slide shows that the impedance values are converted into admittance values to form the Y bus matrix. So as you can see in my slide, each transmission line is first represented using the impedance, where Z is equivalent to the resistance added to the imaginary multiplied by the reactance. After that, the branch admittance is calculated using 1 divided by the impedance calculated. So for example, if you see in the slide, the line between bus 4 and bus 5, the impedance is 0.017 plus imaginary of 0.092 per unit. When this value is converted into admittance, it becomes 1.942 minus imaginary 10.511 per unit. In the Y bus matrix, the off diagonal elements are the negative of the branch admittance. So for the line between bus 4 and bus 5, the Y45 and the Y54 becomes negative 1.942 added with imaginary of 10.511. So on the other hand, for the diagonal elements, all admittance is connected to that bus are added together, including the line charging admittance. For example, bus 4 is connected to bus 1 through the transformer T1, and also to bus 5 and bus 6 through transmission lines. So therefore, Y44 is formed by adding those connected admittance together. So as you can see in figure 2.2, I have constructed the admittance diagram, and also I've constructed the 9 by 9 matrix for the Y bus formation. Overall, the Y bus matrix is the main mathematical model of a network. So it is important because it becomes the foundation for power flow analysis, fault analysis, and the stability assessment in later sections.
For my part, I will present the power flow analysis of the 9-bus power system. Power flow analysis is important because it helps us to understand the steady-state operation of a power network. So in this study, the main parameters observed are the bus voltage magnitude, the voltage angle, real power flow, reactive power flow, and the system loss. So these values are useful to check whether the system can supply the power from the generators to the load bus safely. So three different power flow methods are applied, which are the Gauss-Seidel method, the Newton-Raphson method, and the fast decoupler method. The simulation was carried out using the MATLAB. The 9-bus system data were taken from the reference study and entered it into the MATLAB program. This system used a 100 mega VA base and consists of 3 generators, transformers, transmission lines, and load buses. The simulation was performed under the normal base case condition, which means there will be no fault, no line outage, and no generators outage will apply. The same system data were used for all three methods, so that the comparison is fair and consistent. The acceptable voltage range used in this study is between the 0.9 per unit and 1.1 per unit. This slide shows the MATLAB command window outputs for the three power flow methods. For the Gauss-Seidel method, the simulation converged in 18 iteration. For the Newton-Raphson method, the simulation converged in only 4 iterations. Meanwhile, the fast decoupler method converged in 5 iterations only. So from these outputs, all three methods successfully solved the power flow problem. The result also show the bus voltage magnitude, voltage angle, total generation, total load, line flow, and system losses for each method. From the comparison table, the Gauss-Seidel method required the highest number of iterations, which is the active iterations. This shows that the Gauss-Seidel is able to solve the power flow problem, but it has the slowest convergence. The Newton-Raphson method required only 4 iterations, making it the fastest method in this study. The fast decoupler method converged in 5 iterations and produced results that are almost the same as the Newton-Raphson method. The total line loss for the Newton-Raphson and fast decoupler is 4.8348 megawatts, while the Gauss-Seidel gives the 4.8340 megawatts, which is very close. So overall, all the three methods produced the acceptable result because the voltage magnitudes at all the bus were within the range of 0.9 per unit to 1.1 per unit. The lowest voltage occur at the bus 5, which with a value of 0.99119 per unit, while the highest voltage occur at bus 1, which with a value of 1.0400 per unit. This means that the 9-bus system remains stable under the normal operation condition. Based on the convergence performance, the Newton-Raphson method is the most suitable method because it converges the fastest and gives a very small mismatch. The fast decouple method is also reliable because its result is almost identical to the Newton-Raphson. Gauss-Seidel is acceptable, but it is less efficient because it requires more iterations.
Hello everyone, my name is Darren Hao and my metric number is 215102, and today I'll be presenting on the fault analysis of the WSCC9 bus system. So an introduction, a power system fault is basically a normal condition in which there's a low impedance channel between the phases or between the phase and the ground. And this low impedance channel causes a short circuit between the phases or between the phases and the ground. And in general, there are two kinds of fault. The first kind is the balance fault. In the balance fault, alright, the three-phase fault will affect all the three phases equally. And then the phase current, alright, will have equal magnitudes and are separated by 120 degrees. And then only the positive sequence network will be required during the calculation of a balance fault. And secondly, is the unbalanced fault. In the unbalanced fault, alright, there are three possibilities. The first one is a single line to ground fault, in which it occurs when there are only one phase connected to the ground. And the second possibility is the line to line fault. In the line to line fault, alright, it occurs when there are two phases that are short circuited to each other without involving the ground. And thirdly, is a double line to ground fault. In this fault, alright, it occurs when the two phases are connected to the ground at the same location. So in order to simulate these faults, alright, there are a few data that's needed for the simulation setup. However, right, some data can be reused from the previous section. For example, the system network base values, the generator, transformer, and line parameters, as well as the bus voltages that are obtained from my groupmates that find the bus voltage using the Newton-Raphson method. So the Newton-Raphson method will use the bus voltage that we use as the pre-fault bus voltage during the fault analysis of this section. And there are a few further data that are required for the fault analysis, which is the negative and zero sequence impedance, the transformer grounding configuration, and also the zero, neutral, and fault impedance. So in terms of data initialization, alright, the generator sequence and reactance were taken from the standard WSCC3 machine model, and then I also assume that the positive sequence reactance and the negative sequence reactance are the same, and this is because alright, they are similar passive network components and similar impedance in both of the sequences, and the third negative sequence generator will generate unavailable, so we just assume them to be equal, the positive and negative. Secondly, alright, is a transformer and also the transmission line parameters, and the data will form from the earlier positive sequence parameters and then computed using the assumption for negative sequence, zero sequence, and winding connection and grounding. So for the simulation program, right, after we have all the input that are required to perform the fault analysis, the simulation program consists of the two files. The first file is the fault data, in which it will input all the system topology, the base values, generator transformer, and also the transmission line parameters. And then it also includes the pre-fault bus voltages and also the assumed sequence and grounding data. So after getting all of the data, this program, alright, will organize them into one structured MATLAB variable and then output them as a complete data of the nine buses, including the positive, negative, and zero sequence impedance, also the voltage buses and the transformer grounding information and fault impedance. So basically, it just processes the data into a more structured format, and then all this data is then fed into the second file, which is the fault analysis. So in the fault analysis, alright, this file will take all the data, the process data, and then it will build the positive, negative, and the zero sequence admittance matrices and convert them into the bus impedance matrices, and also apply the four fault types at every bus. And then after applying all the four fault types, we'll convert the calculated sequence currents into the phase currents. So output will be the three sequence bus impedance matrices, and also the four fault current result tables showing the phase A, the phase B, and also the phase C, which is all the phases, current magnitudes, the phase angles, and also the kilo ampere magnitudes for all the faults from all the buses. So this is the result as obtained from the program. So this is the positive, negative, and the zero sequence impedance matrix. And then this is the result of the fault analysis for all the buses for the balanced three-phase fault and also the single line to ground fault. And these results are the line to line fault analysis and the double line to ground fault analysis for all the buses from bus 1 to bus 9. So in a short summary and discussion is that during a three-phase calculation of the three-phase fault and also as seen from the data, the phase behavior is that they are equal currents and they are 120 degrees apart. And also the main network involved is actually only positive sequence because the negative and zero sequence are not involved in the three-phase fault analysis calculation. Secondly is the single line to ground fault. In this fault, alright, the phase behavior is that only faulted phase carries the current, and also alright, the main network involved is all the three types of network. And thirdly is the line to line fault. During this kind of fault, alright, the unfaulted phase current is zero, and then only positive and negative sequence are involved in the calculation. And so lastly is the double line to ground fault. So for this kind of fault, right, the two faulted phases carry current, and then the main network involved are the positive, negative, and zero sequence. This is all the sequence involved. So that's all for my part, and I'll pass on to my roommate.
So thank you. So now for my part, I will present about the stability assessment of the WSCC 9 bus system. So in this section, the main focus is on the static voltage stability. This means we will want to check whether the system can maintain acceptable bus voltages under normal operating condition and when the loading level is increases. So for this assessment, I use the Newton-Raphson method because it gave the fastest and most accurate result in power flow analysis. And the study also includes three main parts, which are voltage stability checking, ability of or PV curve analysis, and weak bus identification. So in power system studies, there are different types of stability. So for this report, the main stability considered is voltage stability. Voltage stability means the ability of the system to maintain acceptable voltages at all bus. And in this study, the bus voltages are checked against the acceptable voltage range of 0.9 pu to 1.1 pu, which is also per unit. If the voltage drop below 0.9 per unit, it considered a voltage violation. Whereas for angle stability is also mentioned in this report, but it only discussed theoretically. This is because angle stability requires a dynamic generator data such as initial constant, damping coefficient, transition reactance, and fault clearing times. And since these data are not provided in our report, so angle stability is not simulated. So this slide shows the base case voltage stability result. So from the bar chart, all bus voltages are within the acceptable range of 0.9 per unit to 1.1 per unit. So the lowest voltage occurs at bus 5 with a value of 0.99119 per unit, and the highest voltage occurs at bus 1 with a value of 1.04 per unit. Since like no bus voltage below 0.9 per unit or above 1.1 per unit, the WSCC 9 bus system is considered stable under the normal base case condition. However, bus 5 has the smallest voltage margin, so it should be monitored when the system loading increases. This slide shows the PV curve result for the load buses. The PV curve shows how the voltage changes as the loading factor increases. So from the graph, the voltage decreases as the load increases. Among bus 5, bus 6, and bus 8, bus 5 drop the fastest at lambda equal 1.75. The bus 5 voltage is 0.90308 per unit, which is still slightly above the minimum limits. However, when lambda increases to 1.80, bus 5 voltage drops to 0.89391 per unit. This is like below the 0.9 per unit limit, so it is considered a voltage violation. Therefore, the first voltage violation occurs between lambda 1.75 and 1.80. So based on the stability assessment, the weakest bus is identified as bus 5. There are three reasons for this. First, bus 5 has the lowest voltage under the base case condition. And second, bus 5 experiences the fastest voltage drop when the loading factors increases. The last one is bus 5 is the first bus to violate the 0.9 per unit voltage limit. This means that the bus 5 is the most sensitive bus in the system. So to improve the voltage stability, reactive power support such as capacitor banks or other voltage support devices can be considered near bus 5. And overall, the base case system is stable, but the voltage security margin reduces as the loading level increases.